Today I'm going to talk about the three chapters which we are going to see how to revise and which topics to focus on before the exam. Uh, so the three chapters here in Unit 7 and Unit 8, that is Chapter 11 is dual nature of radiation and matter, and then in Unit 8 atoms and nuclei. Chapter 12 is atoms and chapter 13 is nuclei. So what is this? These three chapters will combinedly give you 12 marks. So this is a curriculum. In this curriculum, they have mentioned that these three chapters are 12, but the 12 marks for three chapters. But these three chapters are not very hard and also not very long also. So in this manner, I'm going to say what to do and how to revise, and or even those who are starting now can still catch it up. So it is not a problem. Still there is a time of 4 days. So dual nature of radiation and matter. So let us go to the chapter 11 now. So this is chapter 11, dual nature of radiation and matter. So what is there in this chapter? So firstly, the introduction is there, like uh, how uh, how the nature of particles, which we know that for some time we think that for example we take light, it says that sometimes it is a wave and sometimes it is a particle. In some experiments it behaves as a particle, some experiments it will behave as a wave. So these were the summary of few experiments, but these are not with respect to light, but these are with respect to all the particles. Like for example, they have started with uh, the cathode rays and other things. Like they have given some experiments done by J.J. Thomson to calculate the this charge specific charge of the cathode ray. So these are some introduction given. You can just go through that part, but not very much important. So the first thing is electron emission. So the electron emission is nothing but if we consider a metal, there will be a work function for a metal. So what is work function and all, you have to refer this. I'm not going to tell, this is not the detailed session. I'm going to tell the topics and also how to read, that's all. So these work function, they are going to talk about the work function, and also uh, what are the different types of emission, like when the free electrons will be supplied to, uh, for example, there are three types of emission, but in this chapter is concerned, we are concerned with only mainly photoelectric emission. So this emission we are considering with only photoelectric emission. So then that effect is photoelectric effect. So what happens is that there is something called as photoelectric effect, which is proved by several experiments. But even Einstein got a Nobel Prize for this photoelectric effect. So we have to know what is this. So what are the Hertz observations when he did the experiment in 1887? Uh, and also then what are the Halbert's and Lennard's observations? So these were done between 1886 to 1902, and so around 16 years of experiments they have done, and you have to check what this experiment is. And they have found out that something called as threshold frequency. So this is important point. They have found out that something called as threshold frequency exists. Then after that, they have termed after that, these are the main experiments. Then what happened is how we can study the photoelectric effect. The point is that there is some setup for this. This diagram is important because it may be a question, direct question. So experimental study of photoelectric effect. Then how we are going to study the photoelectric effect? This setup and how this explains, this paragraph will explain everything. But this is generally a evacuated glass tube. So you know that in evacuation electrons should not flow, but electrons will flow due to photoelectric effect. There will be a current, and that is what is the experiment. But when the sunlight is passed, due to when the frequency of the light is more than the threshold frequency, then there is a photoelectric effect observed. So these things can be found out by reading, and there are some plots like the current which is measured through ammeter in microampere. So with the intensity of light. So we have to know the difference between intensity and the frequency. Both are not same. Intensity is brightness, I can say, but the frequency is nothing but number of cycles like per second. So the second part is effect of intensity on the light on photocurrent. So this graph, the conclusion is from this graph you can see it is a straight line passing through origin. So you can say that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. So this is a conclusion. Then the third part is effect of potential. What will happen if we plot the photocurrent versus potential? Potential is voltage. So then there is some plots here with the different currents based on the different currents. So there will be something called a stopping potential, and this is like this graph is you can see that from here the current increases and it stops increasing, or the value will remain almost constant. So this is saturation current. And when it happens, and this is all depicted in the experiment, I suggest you to read line by line because that is very important. The minimum negative potential V0 given to the plate A, for which the photocurrent stops or becomes zero, is called cutoff or stopping voltage. So these are the things. Then there is defined as maximum kinetic energy. Then next comes the effect of frequency. You can see this graph is something little like somewhat similar to this graph, but it is not exactly the one, right? So this photoelectric current, and this is versus variation of photoelectric current with collector plate potential for different frequencies. So these graphs are important. I am not going to take much time here now. These graphs and explanations, you have to simplify it, and the two main observations are here. So next part is, I am coming here, the photoelectric effect and the wave theory. So the wave theory was, wave nature was very clearly established in 19th century, by end of 19th century, of light, like phenomena like interference, diffraction and polarization, like you would have studied in the previous chapters, ray optics and wave optics. So these are some phenomena of light. So light is an electromagnetic wave. So what is important here is this para will simply say, it will compare between photoelectric effect and wave theory of light. So what next part is, now this is important from here, Einstein's photoelectric equation, energy quantum of radiation. So here Einstein, he assumed light as a particle. The most important point is light, he assumed that light as a particle which has an energy of h nu. So in which h is a constant and mu is a frequency of light. So there are, light is not a continuous form like we till 19th century they assumed that light was only a wave. But Einstein came, previously there was Planck gave his theory, but Einstein came and used that theory given by Planck to prove the photoelectric effect. To explain the photoelectric effect, that it is due to the particle nature of light. So that is why Einstein got Nobel Prize for this, and also that it is called as Einstein's photoelectric equation. This one, K max, kinetic energy maximum is h nu minus work function of the metal. So kinetic energy is a speed at which energy at which the electron is ejected from the metal. So these are some postulates you have to know, like when these are some conditions, that emission will only occur when the frequency is greater than the threshold frequency. So this is some equations are there, and this then also you can compare the equation that maximum kinetic energy is E into V naught. So both, if we equate both, assuming that the frequency is greater than the threshold frequency, this is a very important. If the one most important point is, if the frequency is of light is less than the frequency threshold frequency, then even if you increase the intensity of the light, it doesn't matter, it is independent of intensity. That is what is the most important conclusion from this photoelectric effect, that whatever may be the intensity, the number of quanta of radiation per unit area per unit time is instantaneous. So low intensity does not mean delay in emission. So this is important, that it is only dependent on the frequency, only on the frequency and the work function, but the frequency is the main thing. So if you can see, this is a straight line equation, you can draw that, from this you can find the slope, and then it will be used to predict some results which were used, which were independent of nature of material. So you can see that h by E both are a constants, universal constants, so they are not dependent on the material. So then the particle nature of light comes, the photon. What is a photon? Here firstly the Planck gave an Planck theory, he gave a Planck theory. So then what happened is, you have to check what is a photon. We can summarize that photon picture of electromagnetic radiation as follows. So interaction of these are some points given that about the photons. And now this is a numerical problem. These numerical problems are important. Definitely one of the problems may come, wave nature of matter. So now comes the wave nature. So again the scientists got confused, like light behaves like a wave, sometimes like a particle. So again one man, de Broglie, came up with a theory called as de Broglie wavelength, that he told that every particle of the nature exhibits a wave like character. So that is what is his argument is, and it will have the particular wavelength of its own. But since the wavelength of the particles like electron, as you can see in this example is very interesting and also important to know the significance of the de Broglie wavelength. So if you see for electron, de Broglie wavelength is in orders of nanometer. But if you see for a ball, which is like 150 gram, which we play, for example cricket. So 150 gram ball has a wavelength of order of 10 power minus 34 meter. So you can see that we cannot find the wave-like behavior through experiments in a ball, but we can find the wave-like behavior of electron because it's in only nanometer. So this is what is a conclusion. So you can see that we cannot measure the beyond experimental measurement. So this is about this chapter. So I can split this chapter into the experiments done by the photoelectric effect, then what are different types of emissions, photoelectric emission, then uh, how we are doing the experiment. So what are the different types of plots in the experiment, like these are all the plots, and you should be able to explain the plots, and these plots may be given even for 1 marks, maybe just like missing value or something like that. So you have to know this, and then the most important part is the photoelectric equation, and also how you have to explain this, and also photoelectric equation followed by what is a particle nature of light. So it will show what are the photons are. These are explaining the photonic picture of light, then the numerical problem, and then the de Broglie wavelength. This wavelength is related to the momentum of the particle. So this is a relation between particle and wave. So he is giving a that he is telling that the photon is assumed as a particle, but it still has a wavelength. So in that way, the particles, light particle or light or electron, sometimes it behaves as a wave, sometimes it behaves as a particle. So this is the conclusion of this chapter here. This problem is important because you may better know, like get the understanding as well. So these are the summary and some symbols, some units, and then exercise. You can go through the exercises, and if you have time you can just see it. So this about the wave nature. And quickly I'll go to the next chapter, atoms. So in atoms, what is there? You all know in 9th standard or 10th standard we read about the different types of J.J. Thomson, then Rutherford, different models. So this is similar. It is just more the elaborate explanation. Here they start with the Rutherford model, because J.J. Thomson model was just a plum pudding model. This is introduction, not much important. Going to the Rutherford model is very important, because they found out that Rutherford found out that nucleus, that according to the entire positive charge and most of the mass of atom is concentrated in a small volume called nucleus. So this is what is the main conclusion, which is nuclear kind of model. So that is why it is called as Rutherford nuclear model, in which nucleus, he found out that nucleus has the most mass, but it is very small part of atom. Atom is very big, but nucleus is small part of it, the center of this. So you can see that this is called as alpha particle scattering experiment. So this was done by his students, Giger and Marson experiment also. So one of their experiments is nothing but simply they direct a source of alpha particles on the gold foil and check the screen, how many times hit the beam has hit the screen. They will check, and what is the point. These are the experiment given. You can check the experiment, but the main conclusion is this graph is telling about the scattering angle. They expected that so much scattering would happen, but the scattering it's only about, the conclusion is only about 0.14% of the incident alpha particles scatter by more than 1%. So this point shows that the most of the atom is empty. So this is what it shows, and also it is, so it to get deflected more than 90%. It is shown 1 in 8,000 deflect by more than 90%. So if to get deflect by 90%, the gold particle is, alpha particle is positive, so it should have a large repulsive force. So it shows that the nucleus is positive. So he found out that positive charge is in nucleus, and in this way he is suggested like solar system kind of model. But you all know there is a drawback for Rutherford model, that you can see it, what is the drawback and those things. Again, the force, magnitude of the force can be found out using this formula. Then alpha particle trajectory, it is a simple para given that how, if the nucleus, when it is near the nucleus, how it behaves. A numerical problem, and just look through that, not much important. Now electron orbits. So what the main point is, Rutherford nuclear model used only classical concepts. So what they have given a Newtonian force only. So the force is given by that electromagnetic force. So this is force of the electron and equal to the centripetal force. They have mentioned it. Not electromagnetics or electrostatic. Next is that relation between the orbit radius and electron velocity, and these are some derivations. Find the total energy and kinetic energy, radius. This derivation is important. Next is the total energy is negative. This implies that electron is bound to nucleus. If E were positive, electron not follow a closed orbit around the nucleus. So this point is important. And numerical problem. Atomic spectra. So like humans have a fingerprint, unique fingerprints. Like that, atoms have the spectra. So spectra of one material is different from the other one, other elements in a periodic table. So how to distinguish? How scientists distinguish between atomic spectra between two different elements like hydrogen or helium? They distinguished by atomic spectra. So by spectra they find that this is an element. So different kinds of emission lines, Lyman, Balmer, Paschen, and they lie in a different regions. Only one is the visible one, and others lie somewhere in ultraviolet or infrared region. So this is absorption spectrum of the material. So after Rutherford, there is next one is Bohr model. The importance of Bohr model is he predicted the behavior of hydrogen atom very good, but he couldn't explain further to more nucleus. Like when more atoms are there in the more protons are there in the nucleus, he couldn't explain the behavior of a atom. He explained the behavior of hydrogen-like atoms, but he couldn't extend it to further elements. So he found some problems. So this is the numerical problem. Then he made some postulates. First postulates was electron could would revolve in a certain stable orbits without the emission of radiant energy. And also the second postulate is it has only some integral multiple of angular momentum are allowed. That such orbits are only allowed. The third part he incorporated a quantum concepts developed by Planck and Einstein. So this is important, that only specific energy levels are allowed. Only some particular energy levels are allowed and not all. So the states this radius and energy, this energy formula, this one is important, minus 13.6 by n square electron volt. Then energy level diagram, n equal to 0, n equal to 1, 2, and what is the values of the energy. Then you can calculate that. So n equal to infinite corresponds to that atom is unbounded to. So this part is then the line spectra. Line spectra is fine. Next question is related to de Broglie's explanation of Bohr's second postulate. So this quantization postulate is the explained by de Broglie. Again, he explained by using standing wave. He showed that there will be a standing wave pattern in the circular orbit, where four de Broglie wavelengths fit into a circumference of the orbit. So this is just an illustration. You can no need not much importance. You can see the formulas. So these are some problems, and this is about this chapter. And the next chapter is nuclei. So you can see that in this lesson there are nothing much here. Alpha particle scattering, Rutherford model, Bohr model, expression of radius, velocity and energy, a hydrogen line spectra only. So that last part is not there. So we have to accordingly you have to see which one is there and which one is not there. This is not important. Up to here it is sufficient to read up to Bohr model. Then here coming to nuclei, composition and size of nucleus. So you have to know what is a nucleus and what is the size. Like it is given in some units. It will be given in the atomic unit. So this has to be there. And then how neutron was discovered, that is okay. Then the size of the nucleus, this formula is there. R is R naught into a power 1 by 3, where R naught is a constant. Then the mass energy and nuclear binding energy. So this famous equation of Einstein, E is equal to mc square, is this is mostly you can find that one of the proofs that energy mass is converted to energy can be found in a nuclear manner, so in the atoms. So this was one of the observation. So you can check what is the energy and how much for example 1 gram of substance, how much is equal to energy. So it is so much of energy. So what is nuclear binding energy? And then this curve, binding energy curve, binding energy per nucleon as a function of mass number. So you can see that binding energy is you can think of binding as the average energy per nucleon to separate its nucleus into individual nucleons. So if we want to separate the protons and neutrons, there is some binding energy. So that is called as binding energy to break the bond. It is not a bond, but it is a force. So that is what is given here. You can draw some conclusions that the constancy of a binding energy in the range is a consequence of the fact that nuclear force is short ranged. So this is the most important conclusion, that you can see between 30 and from here it is almost a constant binding energy, because even though the number of nucleons are increasing, but there is not much increase, no increase in the binding energy because of the range of the nuclear force. So you can see that. And also the fourth point is, consider two very light nuclei when mass number is less than 10 joining to form a heavier nucleus. So the binding energy per nucleon of a fused heavier nuclei is more than the binding energy per nucleon of lighter nuclei. So this is important point. This is used in a fusion. So fusion is the energy source of sun. So you have to know about the fusion. Then nuclear force. So this force, potential energy versus the radius. Yeah, you will know that where is the potential energy maximum and how it is. You can find out it is a short range. You have to know how to explain this graph and draw it. So up to here, this radioactivity is being deleted. So that is how there are only 3 topics in this chapter is concerned. What is a nuclear force? You have to know, and mass energy relation, E is equal to mc square, and what is a mass defect. And then binding energy per nucleon and its variation with mass number. The two curves definitely you can expect one question from these two parts, either this one or in the nuclear force, this curve. So this is it about this video. So these three chapters I have covered, and I will continue in the next chapters in next video.